Now we're going to talk about rolling resistance, why it's important, what it is, and why it is that rolling resistance has so much to do with the speed of our bicycles. You'll learn that by reducing rolling resistance, you can dramatically increase the speed of your bike. It's a lot more complicated than most people think, and I encourage you to do a little bit of research on this subject when we're done. Okay, here we go into rolling resistance, another one of our opposing forces. Now, rolling resistance is shown here, mainly resistance between the tires and the road. Now, it's one common observation of mine is the following. People want to ride a lightweight bike, and they want ultralight wheels. They want aero wheels, ultralight hubs, bladed spokes, carbon rims, all that stuff. And then they train and they lose weight. But when it comes to putting the right tires on the bike to get the optimal benefit of all of the other equipment that they've invested in, they just don't know what to do. They ask anybody's opinion. They go to a bike shop and a mechanic will say, well, we like those tires over there. People buy a lot of those. And somebody will say, okay, give me 2 of those, and put those somewhat unknown tires on that expensive bike with all that equipment and with all of the training you've done. This is a mistake, and here's why. If I compare air resistance and rolling resistance at higher speeds, the resistance from aerodynamic drag is our #1 problem. Rolling resistance is #2. Friction and bump are much less significant. At lower speed, the resistance from the air is the smaller problem compared to rolling resistance. The point of this is that rolling resistance is either our biggest or our second biggest problem to deal with. So it's something to contend with. Here we see a train on a track. This is the lowest rolling resistance you can have, steel wheels on a steel track. When we're cycling, we have varying terrain. In the first case, we're looking here at a track bike, that we have a smooth track, we have minimal rolling resistance. Under that, a road bike riding on hard, smooth, paved road, the rolling resistance is higher. It's somewhat higher, again, under that when we start getting at the mountain bikes with hard packed trail, and then soft dirt has the highest rolling resistance. With 700C tires, we're looking at clincher tires with tubes. These are the most common. They're also the easiest to maintain. These are some tubeless clinchers. There's another possibility. These are a relatively new concept on the market, and these are lighter. There's no tube in them, and these probably have a lower rolling resistance also. Sew-ups are another type of tire. Sew-ups are otherwise known as tubulars. The tube is actually sewn up inside the tire. And if you look at some of those pictures there, you'll see that the tube is inside the tire and that the tire tube combination is glued onto the rim. It's not a clincher situation, so the tire has to be glued to the rim. Rolling resistance for tubulars can be quite low if you have high quality tires and if they are properly glued. Now, with respect to that, if the tire stays on, that should not be the test of whether it's glued properly or not, because you can have a tire stay on, that is not roll off, but still have quite a bit of rolling resistance because the tire can squirm around on the rim if it's not glued properly. To be glued properly, there should be glue all the way across the rim between the rim surface and the base tape on the tire. If that's the case, it won't squirm, but it will be also very hard to get off if you do have a flat tire. Now, the causes of rolling resistance can be broken down into 3 different subcategories. One has to do with the deformation of the tire. When you're riding, every time you have your weight on the tire flattens slightly as it goes through a load-bearing zone, and then it regains its shape as it comes out of the load-bearing zone. This is called a hysteresis cycle. The deformation and then reformation of an object. The hysteresis loss occurs in the form of heat. Only some of the energy returns when the tire regains its shape, so we have a net loss of energy as the tire goes around. There's also rolling resistance loss when it comes to friction between the tube and the tire, and I'm quoting Dave Wilson here, Wilson saying, the energy loss due to the rubbing of 2 materials. the inner tube and the tire against each other, and this is a pretty large source of loss of energy also due to that kind of friction. Maybe this is an argument in favor of tubeless. Tube materials are of two different kinds. Isobutyl rubber, polyisobutylene, is the most common type. These are inexpensive tubes and they're by far the most common. But there's another kind that is made of latex rubber. These are more expensive, but they reportedly have 10 to 15% less rolling resistance than butyl rubber tubes. So maybe this is an option for you to consider to use during races. And the third kind of friction loss that's part of rolling resistance is between the tire and the road. And this has to do with the tread design and the material used. Of these three, deformation of the tire is probably the most important one. Now, each tire has a rating associated with it called the coefficient of rolling resistance. And the force that's necessary to overcome rolling resistance is equal to the coefficient times the weight of the rider and the bike. The lower the coefficient of rolling resistance, the faster will be the bike. And tires come with a range of coefficient values. All the way on the left is our train, the lowest possible coefficient, 0.0002. All the way on the right there is a car tire. Car tires have a fairly high coefficient of rolling resistance. And bicycle tires are in the middle. But even those, there's a pretty big range from the lowest to the highest of bicycle tires. I'll give you two examples of why this makes a difference. Here's an article I found by Rick Ashburn that was written in 2007. He studied what happens in an Ironman triathlon, which starts with a 2.4-mile swim and then 112 miles on a bicycle, and then with the energy you have left, then you just go out and run a marathon. Now, here's what Rick computed, that for a 190-pound rider, and I take two tires of different values of coefficient of rolling resistance. Supposing I ride with one that has a front and rear tire with a coefficient of 0.004, and if I compare that with another tire that has a front and rear coefficient of 0.007, then in the case of the first one with a coefficient of 0.004, the power to overcome that rolling resistance is going to be 30.5 watts. And in the case of the higher coefficient of rolling resistance, for the same weight rider, the power to overcome that force is 53.4 watts. So I have a difference of 22.9 watts of power that I have to put out to go a certain speed simply because of the difference in the coefficient of rolling resistance of two tires. Now what that means is that, let's say after 112 miles at riding 20 miles an hour on my bike in my triathlon part of the Ironman, I will have saved 12 to 13 minutes simply by riding on the tires which have a lower coefficient. And that's about a 5% time reduction, which is rather huge over the course of the triathlon part of an Ironman event. Here's another example here. I had several conversations with a fellow named Doug Wager who lives out in the Midwest someplace. And here's the problem that Doug expressed to me over many phone calls. He said, I go out and I ride with my friend. I can hang with him when we're climbing. We ride side by side, no problem, but I fall behind on the descent. And so we went through a process of trying to troubleshoot this over the phone. I said, well, Doug, why don't you try this or try that and then call me back? What we found out in the end was the problem was just the rolling resistance of his tires, because he tried different tires with a lower coefficient of rolling resistance, and now he's able to keep up with his friend on the descents. So everything else is the same except the different tires on the bike made a big difference in his speed. Rolling resistance is complicated, so navigating your way through this maze is tricky. As I said, there are a lot of articles on the internet. It's worth exploring some of those and doing some of your own research. Investigate, check out some of those articles, look at manufacturers' websites, visit discussion forums, and you'll probably learn quite a bit. I don't think anybody knows everything there is to know about this topic. Another thing you can do is you can do your own testing. Decide what factors are important: cost, brand, durability, puncture resistance, rolling resistance, comfort, traction, aero, and so on. And then go to a bike shop and test some tires and share the results. Let's say you make that pitch to them. If you let me test some of your tires, I'll share with you the results that I get, and you'll be able to learn from that. And then you use your power meter. You pick a safe 1 mile flat loop, and you pick a tire to test. You inflate the tire, and then you ride that loop at, say, at a steady tempo of 20 miles an hour. Record your average power for the loop. Repeat that several times just to make sure there's no irregularities in just that one ride. Repeat it several times, average the results, and then use the same testing protocol with different tire widths, pressures, and tire brands. If you do that, you'll find some good data that will help you understand how you can reduce the rolling resistance by varying not just the brand and model of a tire, but also the width and the pressure. You could also do the same thing by using your power meter by riding a steady power and comparing the times.